The next part we're going to discuss is equipotential lines. For those people who are kind of into geography, you might be able to draw an analogy with contour maps. So the picture I have shown here on the slides is Mount Fuji, and on the right shows a contour map of Mount Fuji. On the contour map here, there's a whole bunch of red lines, and each of those red lines shows a constant height. So for example, this bottom line is labeled 2000. Anywhere on that line, you're at an altitude of 2,000 meters. The next line up is labeled 2250. So when you move to that line, you've gone to a new altitude of 2250. When you go to the next line up, now you're at an altitude of 2,500. So those lines show places where you're at constant height. As you move up and down the hill, your height changes. If those lines were really close together, the height would be changing quickly and it would be steep. If the lines were really spaced out, your height would be changing slowly and the hill would be very shallow. Equipotential lines are like this. They show areas around a charge where the potential is always the same. I know you've done this in 1051, but we'll just do a quick recap before we move into some problems. Let's sketch out some equipotential lines. First of all, let's consider if we have a positive charge here. We know the direction of the electric field lines. They move radially outwards. So I can draw a couple of those in. The next slide, I've got them all drawn nicely in PowerPoint. This one we'll just have to deal with my scribbles. Okay, those are my electric field lines. An equipotential line is a line with constant potential. So equipotential line is constant V. We know that the potential around a point charge is V equals KQ over R. So if we wanted a line with a constant potential, it would be a line with a constant R. So to get a constant potential, you have to be a constant distance away. So an equipotential line around this charge would just be a circle. So this dashed green line is an equipotential line. Okay, let's try and do something more specific with a few numbers. So I'm saying that my charge is equal to 0.11 microcoulombs. I'm going to say that the scale of my graph paper here is every line is 1 meter. Let's draw a few equipotential lines as we go through, and then we'll also make some conclusions about equipotential lines and how they relate to electric fields. For our first equipotential line, so V is equal to KQ over R, I'm going to say that I'd like to draw a line where V is equal to 1,000 volts. So then my R is going to be K times Q divided by V. That's going to be equal to 1 meter. 1 meter. So that's going to be a line that comes around this way. That's my 1,000 volt line. My next line I'd like to draw, I'm going to say, is at 750 volts. So on the last slide, I had my 1,000 volt line. If I want my next potential to be at 750 volts, I will do R is KQ over V. K times Q divided by V is 1.33 meters. So my next equipotential line is just a slightly bigger radius, 750 volts. Okay, next one I'm going to do 500 volts. If my V is equal to 500 volts, then my R is KQ over V is equal to 2 meters. So there's my 1,000 volt line, there's my 750, there's my 500. Another thing about equipotential lines is that they're all equally spaced in potential. I'm spacing mine by 250. My next and last line I will do will be 250 volts. So for this one, my V is 250, my R is KQ over V equals about 4 meters. Yes, I did pick my numbers on purpose so it would be easy to draw. So my first line was my 1,000 volt line, then I had my 750, then I had my 500, and then last I had my 200. .250 volts. Okay, let's make some conclusions about what we see here. Each of these black circles that I drew, those are the equipotential lines. They're lines along which the potential is constant. We see that my equipotential lines are perpendicular to my electric field lines. We see that my equipotential lines, where they're spread out by a lot, the electric field is weak. And when they're close together, my E is strong. So the spacing of the equipotential lines gives you an idea of the strength of your electric field. What else? If you move along some path, just grab a different color. If you move along some path that's parallel to the electric field, your potential changes. So potential changes along this line. But if you move along some path that's perpendicular to your electric field, your potential is constant. Okay, that's another statement that our equipotential lines are perpendicular to our electric field lines. Okay, let's move on to a summary in words. So I've got some nice typed up notes here. The equipotential lines are perpendicular to the electric field lines. The electric field lines always point towards low potential, and we saw that on our picture. And this comes from our definition of potential. Change in potential is minus the integral of E dot ds. So that delta V goes as a negative tells us that our electric field lines point towards lower potential. Next, if our electric field is parallel to our path, that's when we do get a change in potential. So delta V is not 0. And in fact, our delta V is less than 0. So we get a change in potential if we move along a path parallel to the electric field. And that's because in our expression, the integral of E dot ds would be the integral of the magnitude of E times the magnitude of ds times the cosine of 0, and that's non-zero. If your electric field is perpendicular to your ds, then you have a cosine of 90 in your scalar product, and your delta V is equal to 0. So this part goes with the fact that our equipotential lines, our lines of constant potential, are perpendicular to the electric field lines. Next is kind of the flip side of an integral. If delta V is minus E dot ds, then the S component of electric field is minus dV by ds. So if you take the derivative of potential, you get that component of electric field. So we could say that our electric field vector would be the x component, the derivative of v with respect to x, and the y component, the derivative of v with respect to y, and the z component, the derivative of v with respect to z. Okay, so that's how we can find our electric field. Sometimes you just call that the gradient of v. I think that's a summary of everything we talked about. And next I've got a PhET simulation video where their pictures look so much nicer than mine. Here's a PhET simulation now where I put some charges on a grid and I used it to show me the potential in the electric field. So I'm going to put 3 positive charges right on top of each other. The bright red is showing an idea of potential and the white arrows show the electric field. First thing I'm going to do is I'm going to grab my sensor that measures potential and I'm going to put it into a spot where I get to 100 volts. Then I'm going to draw the line. This is a great simulation if you want to try it. I'm going to move it out to 80 volts. Then I'll draw a line there. We see that these are circles, just like we drew in our slides a few minutes ago. Then I move down to 60 volts. You see that that circle is spread out a bit more. My next one is going to be 40 volts because the equipotential lines are always evenly spaced in potential. My next and last one will be 20 volts. And that one is really far away from the charge. Okay, I'll put my potential sensor away and I'll grab my electric field sensor. So this little sensor is going to tell me the electric field. You see as I move along one of those green lines, the electric field is constant. It wibbles a little bit because it's hard to be perfect. But when I move parallel to the electric field, it changes a lot. Where the equipotential lines are close, the electric field was big. Where the lines were far apart, the electric field was small. So I think this shows what I tried to draw in the previous slides. This is a great simulation and I encourage you to try it and get a sense of equipotential maps.